Welcome to the massive open online course on Aspen Plus. In today's lecture, we shall perform a case study on isobutene production plant. The problem statement is something like this. The isobutene will be produced from isobutene flowing at 125 kilomole per hour, 25 degrees centigrade and 5 bar pressure. This is a high pressure operation. The stream is first preheated to 600 degrees centigrade. So from 25 degrees centigrade to 600 degrees centigrade and fed into a catalytic PFR, plug flow reactor. And that plug flow reactor operates at 600 degrees centigrade and 3 bar pressure. So it is entirely vapor phase operation. It follows the reversible reaction of class LHHW. LHHW means it is Langmuir, Hinshelwood, Haugen, Watson. So this is the model. And the reaction rate of that class of model is given as follows, where this is the driving force option and the denominator is the adsorption option. So basically, it relates the adsorption with driving force in the reaction rate. So this is the reaction. This is isobutene, this is isobutene, and in the process it loses hydrogen. So in the bargain we produce hydrogen. Now in this reaction rate we have this data. The K is given by this K, capital K, KEH and KE. All of them are given. Now, here the suffix A is given for isobutene and suffix E is given for isobutene and suffix H has been given for hydrogen. And when both hydrogen and isobutene is there, to denote that we write EH, both the suffix together. And this reaction, the basis is partial pressure. Sometimes we can choose basis as concentration, but here we are choosing the basis as partial pressure. And here you will find the E term, that is the activation energy. The unit is kilojoule per mole. And R value has been given. Generally, R value we write in joules per kilomole K. But here we write it in meter cube bar K mole. And the value is this. So we will use this value while doing the calculation. Now, the PFR has 12 tubes and each one is 450 centimeter long, 10 centimeter in dia, and it is a catalytic reaction. So we have loading of catalyst, 1.2 kg of catalyst with 60% bed voidage. Okay, so we will have the pipelines which are loaded with catalyst and 60% of bed voidage. So basically we have the feed, this is preheated and this is sent to a PFR. Okay, so feed is at 25 degrees centigrade and 5 bar pressure, and here it is preheated to 600 degrees centigrade and 3 bar pressure, And this is the reaction condition in PFR. The PFR configuration has been given. So we are up to this point. Now, the outlet of the PFR is cooled to 85 degrees centigrade before it is passed through a membrane separator where hydrogen is completely separated. The remaining mixture of isobutene and unreacted isobutene is termed as rest. So this is first cooled to 85 degrees centigrade, and then it is passed through a separator where pure hydrogen is separated from the rest. And this rest contains unreacted isobutene plus the product, that is isobutene. And 80% of the rest is recycled back to the PFR after necessary temperature and pressure correction. So this one we will split, and 80% of that will be recycled back to the PFR. And obviously that will be done with some temperature and pressure correction. So we know for pressure correction we have to use a compressor, and for temperature correction we have to use a heater. So after doing that, we can send to a mixer, and that will mix it with the original feed. So this is the complete picture till now. Then we have to replace the preheater with a shortcut exchanger and optimize the heat duty. What does it mean? Here we were using a simple heater. We have to replace this one with a heat exchanger, and we have to compare the heat duty. We need to calculate the heat duty in this configuration, and then we have to replace this one with a heat exchanger, and we have to cut this line, take this stream to preheat this stream, and then outlet of this we will pass to the heater. So this is what we will be doing. And whatever the temperature correction that we will do through this particular heater before sending it to the PFR. So this is the complete picture. Now this 20% remains. Now what we have to do, we have to add a purifier for this 20% of the rest. So first we have to try a flash separator and distillation column, and then we have to perform sensitivity analysis with reflux rate, distillate rate, number of stages, condenser pressure. If they are successful, we are happy. If they are not successful, we have to explore a membrane separator. Okay, so that is our complete task. We shall do this thing later. First we have to do the preliminary part, and then do the recycling and comparison of heat duty, and this will come at the last portion. So let us go to the Aspen Plus simulation window. So first we have to add the components. First we have isobutene. This one, add it. And then we'll have isobutene. Yes, this one. So add this. And finally, we will have hydrogen. So we will say H2. And these two, we can replace it with, say, C4H10. And this one, we can write as C4H8. Okay, so this is isobutene, this is isobutene, and we shall use Peng-Robinson method. Okay, so done. Now let us go to the simulation window. Okay, so let us refer to our diagram. So we need, first we will use a heater, then a PFR, then a cooler, and a separator. So we will have a heater, then another heater over here that we will use as a cooler, and then we will have a PFR. Let us use this icon, and we will have a separator. So let us rename them first. Let us write as H1, this is PFR, this is cooler 1, and this is separator 1. So H1, PFR, C1, and SEP1. Now connect the material streams. Okay, done. Now we have to rename them. So let us rename it as feed. This is H1 out. This is PFR out. This is C1 out. This is this will be pure hydrogen because we have to separate pure hydrogen from the product stream. And this will be rest that has been named in the problem statement itself. So what is the feed condition? Please refer to feed condition. This is 125 kilomole of isobutene, 25 degrees centigrade, 5 bar pressure. So we will have the feed condition. It is 125 kilomole per hour, 25 degrees centigrade, and 5 bar pressure. Then we have to fix the heater. Heater will be 600 degrees centigrade, and it will be 3 bar pressure. So this is 3 bar pressure outlet, and then we will fix the PFR later. Then C1, it will come out at 85 degrees centigrade, and there is no pressure drop. You can refer it. It is said that the outlet of the PFR is cooled at 85 degrees centigrade before it is passed through a membrane separator where H2 is completely separated. So we shall have the separator. This outlet stream H2 will have complete H2, all others will be 0. So that is the separator 1. Now we have to fix PFR. Now, before fixing PFR, let us go and set the reaction. Now, always go and start with a general reaction and then go towards LHHW, that is Langmuir-Hinshelwood-Hausen-Watson. So we start with a general reaction type. So press new. This will be a reversible reaction as it is mentioned, and this is LHHW. Okay, give a name to the reaction, say RX. So here the reaction is, let us refer it once again before we go forward. So this is isobutene converts to isobutene and hydrogen. So isobutene converts to isobutene and hydrogen. Okay. Now we have to take care of the kinetic information. So reaction is reversible. Reacting phase, it is vapor phase. It is mentioned over here. This is an entirely vapor phase reactor. And everywhere we have this PA, PE, pH. So our CI basis will be partial pressure, and we'll use it as bar. And here it is a catalytic reactor, so we will give the weight of the catalyst, and the rate will be calculated on the basis of catalyst weight. Now we have to give this information. So here T0 is not specified, so K will be 8.9 into 10 to the power 5. So 8.9 E5, and E will be 112 kilojoule per mole. So this is 112 kilojoule per mole. Okay, so this is done. Now first let us understand the adsorption part, then we will do the driving force. Reaction rate unit, we will use it as moles per grams per second because everywhere we are using moles. Now adsorption terms we have to give as term 1, term 2, term 3, etc. Where term I means 1, 2, 3, etc. That will be Ki C1 to the power n1, C2 to the power n2, and so on. But in our case, we have got, this is our term 1, this is term 2, and this is term 3. And in our case, we do not have the basis C, we have the basis of partial pressure. So KEH will be, in our case, term 2, it will be Ki Pi1 to the power n1, I2 to the power n2, etc. So we have to write it in that form, this C1, C2, etc. So we have three terms. So this is for component butene and this is for hydrogen. Term 1, we have 0 because we do not have any concentration exponent. Okay, term 1 is 1 only. There is no concentration exponent over there. So we write 0. Term 2, we have concentration or pressure exponent 1 for both P to the power 1 and pH to the power 1. So we have both 1 and 1. And term 3, we have concentration exponent of only isobutene, not hydrogen. So we shall give only for butene, this is 1. For hydrogen, there is nothing, 0. Okay. And adsorption expression exponent, this is also 1, because at the denominator, the whole term is 1. Now, term 1, what is term 1? We have to give this information to Aspen Plus in the form of ln k, I mean whether it is k, ke, keh, anything, ln k will be a plus b by t plus c ln t plus d into t. So it will be in this form. So all of them, we have to convert it in this form. So in the first case, for KEH, it will be ln KEH will be ln of 1.2 into 10 to the power 6 plus minus 79 by R. So it will be minus 79 by 8.314 into 10 to the power minus 5 by T plus 0 plus 0. So C and D will be 0 for this particular expression, and this one will be A, this one will be B. And if you calculate, your A will be 13.9978 and your B will be minus 950204. So we have to enter these two terms in Aspen Plus. So just go to Aspen Plus window. So for term 1, when it is equal to 1, then A is equal to 0, B is equal to 0, C is equal to 0, and D is equal to 0. So for all of them, we will have 0 only. So K1, so term 1 is equal to 1. And term 2, as we have calculated just now, it will be 13.9978 and B will be minus 950204. Okay, so just see, it has come in this fashion. So K2 is equal to 1.2 into 10 to the power 6, 1.2 into 10 to the power 6, then e to the power minus 79 by R. So 79 by R is this one only. Okay. So similarly, the third term, it will have this one. So it will be, A will be ln of 2.5 into 10 to the power 5 and B will be minus 87 by 8.314 into 10 to the power minus 5. So if you calculate that, your A will be 12.4292 and this will be minus 1046428. So insert these two figures into Aspen Plus simulation window. So your A is equal to 12.4292, and this one is minus 1046428. Okay, so this is done. So all the three terms have been given. So you compare your rate expression, this kinetic factor, driving force, and adsorption. So we have already fixed up the adsorption and kinetic factor K, and we have to give the driving force now. So for driving force, we already have the data with us. Here, it is simply 1. We'll directly give these values. Specify rate constant and concentration exponents for forward and reverse reaction. So for forward reaction, exponent is 1 because it is only PA, and for this is 0 and this is 0, and all the coefficients are 0 as well. And for reverse reaction, it is PE PH by K, so there will be no reactant over there. For products, there are 2 exponents, and here also the coefficients of the driving force are like this. Okay, so we have set the reaction, done. So R1 we have fixed. Now go back to PFR. So set up PFR. The reactor operates at constant temperature of 600 degrees centigrade. So reactor with specified temperature of 600 degrees centigrade. The configuration, it's a multi-tube reactor. It has 12 tubes, each one is 450 centimeter long and 10 centimeter in dia, loaded with 1.2 kg of catalyst with 60% bed voidage. So we have to insert this information. So this is multi-tube reactor with 12 tubes. The length is 450 centimeter and dia is 10 centimeter. And the reactions already we have defined, just press it over here. Pressure, it operates at 3 bar pressure. PFR operates at 3 bar pressure, entirely vapor phase. And then catalyst. Catalyst is 1.2 kg of catalyst loading is there with bed voidage 60%. Okay, that's how we specify the PFR. Now everything is set. Let us run. Okay, so the run is complete. Just click the temperature, pressure, and molar flow rate. Yeah, so 125 was the molar flow rate at the inlet, and we have got 188 of molar flow rate in the PFR out. And we have got 62 kilomole per hour of hydrogen. This line will be full of hydrogen, and that's how the separation unit has been designed. So here we have only hydrogen, 62.5 kilomoles per hour, and the rest, it will be only isobutene and isobutane unreacted, and they are of equal proportion. Now we have to take out 80% of this and recycle it back. Okay, so what we need to do, we need to use a splitter over here, and we need to use a mixer over here. Okay, so first we make some room for this one. So we reconnect destination to mixer, and we connect this with this. Then we connect this with this, and this is the 20% of rest. And we have to recycle it to the PFR after temperature and pressure correction. Now let us see what is the pressure over here. Pressure is 3 bar, and here also pressure is 3 bar. So there will be no necessity of any compressor over here. Okay, now we shall change the simulation a bit, because later we are going to replace this heater with a heat exchanger and calculate the change of heat duty. Now this heater not only heats, but it changes the pressure also. So the total duty will be more than just heat transfer duty. So what we will do, we will keep here as 5 atmosphere only, and let the PFR do the job of changing the pressure. Okay, so we shall make it 0 pressure drop. Split block needs extra outlet, so yeah, we'll name them later. And we have to set split fraction of 0.2, that means 20%, to this side. Okay, now it will run. Yeah. Now we have to do certain temperature and pressure correction. So for that we shall need one pressure changer over here and one exchanger, not exchanger, one heater over here. And first we shall rotate the icon, flip horizontally, and this one also flip horizontal. Yeah. Now connect this one at this end, then connect this one to this end, this one to this end. Right. Now let us change the name. So this is our product. This is recycle. Okay. Reconnect source at this point. Okay. So this is compressor. This is heater 2. Okay, heater 2 already exists. Fine. So we are using H2 for hydrogen. So we have to write heat 2 Okay, this one is come out, and this is He2 out. Okay, renaming is complete. We have to assign the values in compressor. So this is a compressor of type isentropic, and the discharge pressure should be 5 bar so that it mixes with the line. Okay, it mixes with this line. And this heater output, we do not know what should be the temperature of the heater output. So let us say that our heater temperature is, say, 600 degrees centigrade and no pressure drop. So if we run it now, okay, so the simulation is complete. Now we have to check the heat duty. So we find the heat duty of H1 is this, PFR this, C1 this, and HE2 heat duty is this. So this plus this plus this plus this. So total heat duty, this will be 7616285. So much of calorie per second. So this much of heat duty will be required for running this process. Now we have to replace this heater with a heat exchanger. So the idea is that we are using one heater to increase the temperature from 25 degrees centigrade to 600 degrees centigrade, a cooler to cool down from 600 degrees centigrade to 85 degrees centigrade, and another heater to increase the heat from 106 degrees centigrade to 600 degrees centigrade. So why to use 3 heaters like this? Rather, we can use some heat exchanger which can exchange the heat between 2 process streams and minimize the heat loss and save some money for heating. So for that, we have decided to replace this particular heater with a shortcut exchanger. So this will be regarded as a preheater, and later we have to optimize its heat duty. So we replace this. First, let us cut this heater and then insert a heatex. So let us connect this cold stream. This is cold out. And then we reconnect this stream to this destination, and we connect these 2 ends. Okay, so this is what we have. So we are using the heat of the process stream that is coming out from the reactor to preheat the feed. And whatever the temperature this stream will come out, that will be corrected with this heater. Now, obviously, if our hot stream inlet is 600 degrees centigrade, then cold stream outlet cannot be equal to 600 degrees centigrade. It should be less than that. So we'll specify the cold stream outlet to be, say, 500 degrees centigrade or 550 degrees centigrade. Run this. Okay, so it has converged, but there is one problem over here. It has decreased the inlet temperature of the reactor to 589. Although the reactor is operating at 600 degrees centigrade, and that is the reason why this stream is coming out at 600 degrees centigrade, but the PFR is using its own heating mechanism in order to increase this temperature from 589 to 600 degrees centigrade. But we do not want that. We want the stream to carry material at 600 degrees centigrade itself. Now, this is with a temperature of 550 degrees centigrade, and this heater is sending the stream at 600 degrees centigrade. So this particular mixer will have a combined fluid which will have 589 degrees centigrade. Now what we need to do, we need to fix this temperature at 600 degrees centigrade by manipulating this temperature to whatever. Okay, so we will use a design spec for that, which will fix this particular heat temperature by manipulating this one. So for that, let us rename it first. Let us rename it as HeatX. Let us rename it as mixer out. Okay, so we want to fix the temperature of M out by manipulating temperature of H2 out. So for that, let us use a design specification. Press new. So define M out temp, which is a stream variable of stream M out. The temperature is the variable. So M out temp, its target should be 600 degrees centigrade with a tolerance, say 001. And we will vary the block variable. Which block? It should be HE2, and the variable again, it will be the temperature. And obviously it will not be less than 600. So let us start with 600 and end with, say, 700. So we expect that the desired temperature will lie between 600 and 700. So this is our DS1 fixed. So run. Yes, now it is done. So just check, the temperature becomes 614 degrees centigrade. That means if the temperature of H2 out is 614 degrees centigrade and H1 out is 550 degrees centigrade, then this mixer will send out a combined flow which will be of 600 degrees centigrade temperature. And this is the ideal temperature for the PFR to work. Okay, so we have fixed our HE2 out at temperature 614 degrees centigrade, and there is no need of design spec, so we shall just deactivate this. Okay, so run it once again. Done. Okay, so we shall calculate this heat duty once again. So this is this much, this one, and this one. So this plus this plus this plus this, and the total will be 6761623 calorie per second. So this will be the total heat duty by using the heat exchanger. Now compare this with this. obviously there will be a reduction. How much? The reduction will be 6761623 by 7616285 into 100%. So it will be 88.77%. That means instead of using heater, if you use a heat exchanger, then you can save around 11.23%. So by using a heat exchanger in place of a heater, we can save 11.23% of heat duty. Now our job is not over. We have to optimize this heat. Now for optimization, you can add up this particular stream plus this particular stream plus this particular stream plus this particular stream and join them all as the objective function. So you can open a model analysis tool, optimization, O1, Q heat X. It's a block variable. Which block? It is the heat X block. The variable will be the calculated exchanger heat duty. Okay. So similarly, so first let us copy and then paste, paste, paste. So let us change it to QPFR, and all of them will remain same except in place of heat X you put PFR. This one rename it as C1, and in place of heat X you will have C1, and this one HE2, in place of heat X it will be HE2. So we have defined the calculated heat of heat X, PFR, C1 and HE2. And remember, this one is positive, this one is positive, while this one is negative. This one is also positive. So C1 is a cooler. So we will use Q heat X plus Q PFR minus Q C1 because this is a cooler, and plus Q HE2. So this one we have to minimize. And what we need to vary? We need to vary the cold stream outlet flow rate of heat exchanger. So this will be a block variable. Which block? The heat X. Which variable? The cold stream specified outlet temperature of cold stream. So the lower limit we give 500 and upper limit we give 580, and as we will do the optimization we still need the design specification, right? So we will activate the design specification. We can fix this a little bit higher, and this is a little bit lower. Okay. Now let us run the optimization. So it has rather converged very fast. Go to the result. So it has reached 580. So it has reached the upper bound. That means as you go closer and closer to 600 degrees centigrade, the total heat duty will be better. And what is the objective function? The total is 6709519. So it is even less than the figure that we had obtained before. Obviously, if the cold stream outlet temperature is higher, that means the feed stream is preheated more, so the load on HE2 to correct the temperature of the combined feed will be less. So the total heat duty will be less. So this is quite expected and we are happy with the result. Now we shall again deactivate design spec, we'll deactivate optimization. Okay, so we have already done this one. So now we have to add a purifier for the 20% of the rest. So for that, let us see what is there in 20% rest. So just go and check this stream product. And here we'll find total 125 moles, out of which 34.4 kilomole is unreacted butane and 90.59 kilomole is the isobutene, the product. Now suppose we place a flash tank. So write flash here, it is evap, this is flick, okay, and the flash tank, let us say its heat duty is 0 and pressure drop is also 0. So if we run it, okay, so you can see the temperature is 85 degrees centigrade and the entire material has gone up 125 kilomole per hour, whereas the bottom there is 0, nothing is there. So let us change the temperature. So with 0 heat duty it won't work. Let us decrease the temperature to 50 degrees centigrade and run it. Still everything is going at the top, nothing in the bottom. And check the temperature. Let us cool down some more, say 10 degrees centigrade. Well, now everything has come down to the bottom, nothing is at the top. Okay, so let us do a sensitivity analysis from 10 degrees centigrade to 50 degrees centigrade and check how the fluid moves in the flash tank. So go to the model analysis tool, sensitivity analysis, create a new, and then we have to vary the temperature of block. Which block? Flash. And what do we vary? The temperature from 10 degrees centigrade to 50 degrees centigrade with an increment of 1 degree. We'll define the flow rate, so vapor flow rate, which is a molar flow rate of stream evap of component C4H8. Okay, and also we'll check another flow, that is total flow. So which will be a stream variable? Which stream? It is evap. And what variable? The molar flow rate. So this will be a total flow, this will be only the isobutene flow, and we will tabulate both of them. Run. Okay, result is available. Check. Wow. So from 10 degrees centigrade to 23 degrees centigrade, there is no flow at the top, and at 24 degrees centigrade everything comes to the top. So Let us fine tune, say 23 to 24. So go to the sensitivity analysis once again, check it. From 23 to 24, run with 0.01 and run once again. 100 points will be there. Again we see so from 23.27 to 23.4. So within these two temperature, everything is going either top or at the bottom. And really we cannot control it, because if the temperature is slightly here and there, then either the entire thing will go down or it will go up. So I don't think that using a distillation column or a separation column will help, okay, because the content is very, very sensitive to temperature. So I'm sure that it will not work, but still let us try once. Let us cut this and replace it with a column. Say, let us take a rad frac. And let us connect this thing with this one, this thing with partial distillate, this thing with a flake. Yes. So this is our column, and we have to define various things at column. So let us use 25 stages, condenser, maybe partial vapor, and distillate rate. Let us use 70, because we need 70 kilomole per hour out of 125 kilomole per hour. Reflux ratio, let us use 3. Streams, feed stream, let us put at 12th stage. And pressure, let us operate at, say, 3 bar pressure. Let us not change it, because it is at 3 bar, the reactor output. And run. So this is the result. If you want to run this column with the expected output, you need to attain a temperature of 23.09 degrees centigrade at the condenser and 23.7 degrees centigrade at the reboiler. Now you can very well understand that it is not possible for a 25 stages column to maintain in such a fine temperature difference that at the bottom it is 23.7 and at the top it is 23.09. So the option of distillation column is at all not possible. So in the problem statement, it is said that we can try out sensitivity analysis with reflux rate, distillate rate, number of stages, condenser pressure, etc. We have tried flash separator, it didn't work. We tried distillation column, and it seems it won't work. But still, we can do some sensitivity analysis with these things. For that, again, we have to go to the sensitivity analysis tool. So S1. So we'll vary, say, reflux rate. So it is a block variable. Which block? It is column. And which variable? It should be reflux ratio. So it is mole RR. So molar reflux ratio. And we have used reflux ratio 3. So let us start from 1 and do it up to 5. with an increment of say 0.1 and check how the V flow and T flow work. So what is V flow? V flow is the molar flow rate of stream FVAP and component isobutene. And T flow is this stream variable of stream FVAP, and the variable is molar flow. And then we shall fill the variable tablet. Okay. Now run. Okay, so it has run. Obviously this will come with lot of errors because it cannot work in that range, I believe. Actually errors are there at the first 4 cases. So from reflux ratio 1 to 1.3 it doesn't work. So perhaps 1.4 is the minimum reflux ratio, and that is the reason why the simulation is not possible for these 4 reflux ratios. Okay, now never bother, let us analyze. When it is 1.4 it is 48.7952, and when it is 5 it is 43. So the kilomole per hour doesn't change much. So the purity of isobutene doesn't change much. It is 43 out of 125, so it is not much. So we have tried with reflux ratio, that didn't work. So you can try with reflux rate, displacement rate, number of stages, and condenser pressure, because by now you have learned sensitivity analysis quite well. So I will not do over here. You can do it yourself as a practice, and I am sure that even by doing the sensitivity analysis you won't get any better result than whatever we have got just now through reflux ratio. So in short, neither flash separator nor a distillation column will be an ideal candidate for the purification of C4H8 from the mixture of C4H8 and C4H10. So only instrument that you can use is a membrane separator. Now by saying membrane separator, obviously we do not have a proper model of a membrane separator, so you can just use a simple separator to separate them. So basically you have to remove this one and place one membrane separator, and through that membrane separator you can separate C4H8 and unreacted C4H10, and that unreacted C4H10 you can recycle and check what is the increase in percentage of production of isobutene. Okay, so that portion I keep it as a practice task for you, because by now you might have learned many things about Aspen Plus, so this portion it will be very easy for you to do. Okay, so with that we come to an end of this case study, and we'll come back with another interesting case study in the next lecture. Thank you.